So we've had 4 lectures where we've part 1, which is a simple problem tackled by simple methods. And so it happened to be the driven cavity at a Reynolds number of 10. We had a little discussion about the physics and the mathematics that was in the question to be tackled. And there were 2 methods of dealing with the awkward pressure, stream function vorticity, which avoids the pressure, and then the primitive variables, the last lecture, where it is quite complicated, because you should probably end up on a staggered grid, and then there are rather subtleties in using the staggered grid. So I've used finite differences, which perhaps many of you have come across before. There was a Poisson solver, and I gave one simple speed up, an order of magnitude speed up in solving the Poisson problem. Poisson problem occurs in both the stream function and vorticity, and also in the primitive variables. You can't avoid solving a Poisson problem, and by inserting one single line of code, you can give an order of magnitude improvement, but there are even better things that will happen in this part 2 that we're going into. So we found in time stepping there are issues of numerical instability. All the time there are issues of accuracy, and if you design a code to be second order accurate, does it really deliver answers which are second order accurate? That is a good test that there's not a bug in the code. Okay, and then eventually I got some results, and they were sensible results. I tried to interpret them in terms of physics. Do I expect to see these patterns of flow? So that's a simple problem by simple means. And now we're going to pick up the general issues of discretization, time stepping, and linear algebra, and go to a more sophisticated level. So you have simple ways of tackling things, and there are, you might say, better things. It's not quite clear whether you should use the word better. They certainly could be faster. They certainly could be more accurate. They're also going to be certainly more complicated. More complicated code is more opportunities for going wrong. So given a new physics problem you're trying to solve, it's rather a good idea to start with the simplest possible method you can think of. And when you find that it's too slow or you find it's not accurate enough, then switch in a more sophisticated treatment. Okay, so the part 2, dealing with these general issues, as I say, there's discretization. How do you turn a differential equation, which has got continuous data, into a finite problem for a finite computer? We've done used finite differences where the representation is by some spot data over a grid. There is the possibility of using finite elements that you may have heard of or use, which I'll explain, and spectral methods, sort of Fourier analysis approach. They have advantages and disadvantages. And there are things sitting in between that I'll get to in the part 3 of specialized topic. There are things called splines, which are sort of halfway between, well, they're vaguely associated with finite element representations. And there are wavelets, which are a sort of spectral representation. We'll get onto those much later. There's time stepping, and we have to think a lot about pressure. How do you handle pressure? And faster, and there are things called implicit time steppers. And then solving large linear equations, the Poisson problem, and also eigenvalues. Part 3, so there's 6 lectures on part 2, and then there's a collection of specialized topics in part 3, which come to about 6 lectures, I think. The number of specialized topics I give depends on which year I give this lecture course and what they are. It comes and goes. Okay, so finite differences. We've had the simplest things, and let's look a little more. So we had the first derivative and the second derivative. Central differencing is a good idea because the accuracy is delta x squared. There are higher derivatives which occasionally you need. So the third derivative can be calculated by using the rule for the first derivative applied to the second derivative. So if you want the third derivative, you just substitute in the second derivative into that expression, and you end up with this longer expression of 1 minus 2 plus 2 minus 1. And that is second order accurate, it's central differences. And similarly, the fourth derivative can be calculated by using the formula for the second derivative applied to the second derivative. Just substitute in and generate a lot of numbers. So 1, 4, 6, 4, 1. The even numbers are in fact the Pascal triangle numbers. If you think about how they worked out, it's pretty obvious they're going to be the Pascal triangle. If you think a little more, the odd ones are sort of the Pascal triangle doubled, because there's twice. It's roughly this one, but twice in a complicated way. Okay, so that's second order accurate. For higher derivatives, the first, second, third, and fourth, you can keep going. If we look carefully at what the errors are, I've said it's second order accurate. Let's derive the formula for what is the error. You can then use your understanding of the error to go from second order accurate to fourth order accurate. So you make a Taylor series expansion around the point I by adding a delta x to the point I. So I should point to both sides, shouldn't I? So that's the extra distance times the first derivative, a half delta x squared. The second derivative, a sixth of the third derivative, a 24th of the fourth derivative. You just have to have lots and lots of terms. So you want it's a good idea to turn the paper sideways so you can write lots of terms down. So then if we're thinking of the first derivative, which is the difference of the point in front and the point behind, for the point behind, that would be a minus delta x. We have just the minus on the delta x and the delta x cubed terms. And then when we subtract them, we just pick up the odd terms there. There's 2 delta x and a third of delta x cubed, the third derivative. So we can see that if we were to divide by 2 delta x, we'd have the first derivative and this delta x squared error. Okay, so dividing by 2 delta x, we would have the first derivative, and then there'll be a delta x squared error. And we have an exact expression. It's a third of the third derivative. And just a minute ago, I told you what the third derivative was. Here's the third derivative. So if we substitute in the third derivative into the expression of the error, we end up with this expression. There are other ways of deriving this complicated expression, but this is a formula for the first derivative with fourth order accuracy. You can play the same trick with the second derivative, that is to substitute the Taylor series expansion into the expression for the second derivative, in which case all the odd terms drop out and you just have the even terms in the Taylor series. So we'd pick up the first term, but that all cancels, the second term and the fourth term. And you end up with an expression for the second derivative, which involves not only the point and the point in front and the point behind, but 2 in front and 2 behind. And some horrible, complicated coefficients. And there must be a general formula for these coefficients, but I don't know what it is. So you get these complicated expressions, you should think, have I made a mistake in the algebra? And to find out if you made a mistake, you should test whether they're working. So for this first derivative here, if I feed in the function f is a constant, 1 is the function x, is x squared, is x cubed, x fourth. If it's fourth order accuracy, and it's supposed to tell me the derivative. The derivative of all those functions, 1, x squared, x cubed, x fourth, at x equals 0 is 0, 1, 0, 0, 0. Okay, shall we try one? Let's try a constant. That's always easy. So this is minus a 12th plus a 12th. That's 0. Plus 2/3 minus 2/3. So 1 works. You get 0. Now let's try for x. What will happen is this will be 1. This will be 1. That's be minus 1. That'll be minus 2. So as we go down, it will be, I'm afraid we just have to do this. This is minus a third plus 2/3. So that is going to be 1/3. This is not working well, is it? Yeah, that's working. Okay. Let's have faith in us. It ought to work out. Off we go again. So if I have put in x, I've got here 2. It's 2. So this is minus a 1/6 plus 2/3, which is a half, minus 2/3, which is, sorry, this is plus. What's a half plus 2/3? Is 1 is 7/6 minus, and this is minus 2, so this is minus a 1/6, so that's 1. Oh, got there. It's pretty obvious that x squared is going to deliver 0 because of the, in any even function you put in, the minus will cancel with the plus, the minus will cancel with the plus. So we don't have to do x squared. Can we do x cubed? Great concentration. Ready? X cubed. So this would be 1, and then at I plus 2, it will be 8. Okay, minus 8/12 is minus 2/3. Minus 2/3 plus 2/3 is 0. Oh, it's going to go out to 0. Right, can we do x to the 4th? All right, we can do x to the 4th. So 2 to the power 4 is 16. So what's 16/12? This looks bad, doesn't it? No, it's 16/12. Oh, it's an even function. I don't have to do it. It's an even function. Right. Okay. So I stumbled through those. You on a sheet of paper with not 30 people facing you would do a bit better. Quicker. Okay, so what we've got here are expressions for the first and second derivatives at delta x fourth accuracy. So these are central differencing. It's very good idea to do central differencing because it turns out it's always 1 order of magnitude more accurate than you deserve. However, there are problems that's called boundaries. So if you want to work out the second derivative on the boundary, you don't have 2 points outside the domain. So these are called one-sided derivatives. You can only use information on one side, the interior. So how do we get on with that? So we've used the first derivative is 1 point inside minus the boundary value divided by delta x, and that's only first order accurate because it's not central differencing. It's the first derivative worked out at the half point. And so we also can do the second derivative, effectively the second derivative at 1 point into the interior, which is not where we wanted it to be. So the second derivative is centrally differenced there, but we wanted it at 0, so it's a first order accurate, first order error, and similarly the third derivative. But we can play the same tricks as before. You make an error analysis, Taylor series expansion, find out what the error is, and if you use the second derivative, that's this one, which is only first order accurate, if we substitute that into here, we can then work out what the first derivative is at second order accuracy. So I used that several times in the last 2 days. I actually derived this second order accurate first derivative by a different mean. So I said I knew the first derivative at 1 point in and at 2 points in, and so I could do a linear extrapolation to find it on the boundary. So that's another way of deriving these. More accurate methods is to use central difference, which is more accurate, and do a linear extrapolation. Okay. So in the second, I think I also used the second derivative at and on the boundary using the boundary value and 3 interior points to get a second order accurate. If we were in the interior and doing higher order, if we were in the interior, an expression similar to this, but central difference, would be at 4th order accuracy. I think that's 3rd order accurate. Okay, so you sometimes have to use one-sided differentiation when you're on the boundary. Okay, I've assumed all the time, without telling you, that the points are equispaced, and it's very wise to have equispaced points because it gives you second order accurately with central differencing. If you have non-equispaced points, you don't have central differencing. So how do you treat non-equispaced points? Well, if you wanted, this is a general expression, if you wanted the kth derivative at accuracy delta x to the power L, that strange symbol is the strange font, to the power L, then what you do is you fit a polynomial of degree k plus L through k plus L plus 1 points. The plus 1 is because of the constant term. So, and the points are x, the x naught, the point place of interest, plus nearby points I'm saying are delta xi away. And there's different values of delta x for different points, these non-equispaced points. So you just fit a polynomial, a constant plus a linear term plus a quadratic term up to a term of order x to the k plus L to the data points where you've got different values of f. And you do that, if you're sensible, by a computer package, something like Maple or Does MATLAB do that, such good jobs? Mathematic's got it. Does MATLAB have Maple built in it? So you can get computers to do algebra for you as well as doing arithmetic. So you get something like that to deliver the expressions for the coefficients in terms of the many different spacings and the data points, the value of the function at these particular points. And then the kth derivative is the last, or is the term at ak halfway down this line here, factorial k for differentiating k times. And there are the higher terms going on, and that's giving you the accuracy at the higher level. I've only done this about 4 times, so it's an unusual thing to do. But sometimes you get given data, you read a paper, and they give you data at unequal points, and you just have to use it to do something. So that's what can be done. Okay, so as it says here, central differencing with equispaced points is a jolly good idea because it gives you 1 more degree of accuracy than you expect. This formula would say you get it, say, to 3rd order, but if it happened to be central differencing with equispaced points, it would be 4th order accurate. Okay. So I've shown you how to get from 2nd order to 4th order accuracy, and you can play the same trick and get 6th order accuracy if you really want, but it's a bad idea because you get involved with points further and further away when the derivative you're trying to work out is substantially different, unless you have a very fine grid. So you don't want to use even higher order accurate methods, and there are better things to do. So what happens with fitting higher and higher order polynomials is that the polynomial function does certainly fit the data points, but between the data points it goes wild. So it can be several orders of magnitude different to the data in between the data points. And that's not good for you. So, so there are better things called splines, which are localized polynomials. So you can fit a third-order polynomial over one interval, a different third-order polynomial over the next interval, and a different one over the next one, and you stick them together, you knot them together, and that introduces a weak amount of information from a long distance away, and it gives you a very nice smooth curve in between the data points, and it is quite accurate. It's third order, it may be fourth order accurate cubic splines. So there are splines that do better, and finite elements, well, I'm going to talk, right, let's move on. So, our Poisson problem, it crops up all the time, so it crops up in the lectures from time to time. We'd like to make a fourth order accurate Poisson solver, and I'm starting in one dimension to get the idea across, and then we'll switch to 2 dimensions, which is a little more complicated. So in 1 dimension, the Poisson equation is 2 derivatives of, using phi equals rho. That's del squared phi equals rho in 1 dimension. So we have an expression for the second derivative of phi, which is fourth order accurate, and it's at minus a 12th, 4/3, minus 5 halves, plus 4/3, minus a 12th. And you can use that to solve the Poisson problem to accuracy delta x to the 4th. But there is a difficulty. This wide numerical molecule going 2 points away from the point of interest starts to get larger errors. It's delta x to the 4th, but perhaps times quite a large number. And also, we've got to face up, what do you do at the boundary? So we don't evaluate the function on the boundary, but we have to satisfy the governing equation, 1 point and 2 points in from the boundary, and those 2 points will use information which is outside the boundary with this wide numerical molecule. We can do better with what's called a compact fourth order solver. So if we think about our normal second derivative finite difference expression, the normal expression for the second derivative in finite differences, what is it? It is the second derivative, and there's a delta x squared error involving the fourth derivative of the function. And now the clever trick is, I go away and find out what is the fourth derivative of the function. Here's the fourth derivative of the function. Up there I'm told what the second derivative is. So why don't I differentiate that twice and get 4 derivatives of phi equal 2 derivatives of rho? So I can then put 2 derivatives of rho in there. And for 2 derivatives of rho, I can use our expression for second order, our expression for the second derivative, this expression for the second derivative, but on rho, and it would be second order accurate, but it's already multiplied by 2 delta x's, so we're ending up at delta x to the 4th. Okay, so that's what this is saying. We have the expression for the second derivative. Of phi, so the fourth derivative of phi is the second derivative of rho, and then this is the second derivative of rho with finite differences with a delta x squared error, times the delta x squared error there will give me a delta x to the 4th error. So that is a compact form. It is only using 1 data point either side of the point of interest, but it's fourth order accurate. And, right, so that's in 1 dimension. We're always in 2 dimensions or 3. What happens in 3 dimensions? Well, we use the same trick that we know that del squared phi is equal to rho. So del squared of rho is del to the 4th. Del squared of phi. And del squared of phi is just 4 derivatives, 2 cross derivatives, and 4 derivatives. That's actually a little problem. It's not what define our finite difference numerical molecule for the Laplacian gives, so I've not divided by delta x squared, it gives me del squared of phi, and it gives me, because I'm taking an x derivative, I get a fourth derivative in x error, and because I'm taking a y derivative, I get a fourth derivative in y. So my error term involves the fourth derivatives with respect to x and with respect to y, but I don't get the cross term. So knowing del squared of rho is not much help at the moment. And then the nice thing is, this is one way of working out the Laplacian of phi. I can rotate it by 45 degrees, this numerical molecule. If I rotate that numerical molecule by 45 degrees, I have this one, which uses not the same value of j and I the same value of j and I plus 1, but it uses I plus 1, j plus 1. And equally on the others. That actually gives you twice the second derivative. And the expression for the errors, you have to work quite hard to find out what they are, is a fourth derivative with respect to x, a fourth derivative with respect to y, and 6 cross terms. Okay, so we're in business. So if we take a third of the second expression and 2/3 of the first expression, we'll get 4 derivatives of x, 2 lots of the cross term, and 1 lot of the fourth derivative in y. So that leaves us to this complicated object. This is taking 1/3 of this and 2/3 of that. And that gives me del squared of rho, and then this is our standard numerical operator of del squared of rho, and there's a factor of a 6th, and so I take, okay, I'm sure this is right. So that has to end up as a 12th when we add it. So this is a 12th here. Okay. I don't want all of del squared of rho, I want 2/3 of del squared of rho. Okay, so that has an error, a fourth order error, and I can solve that numerically. And this is with my little test problem. I feed it rho is sine x sine y with a factor of 2 pi squared. So I know the solution is phi is equal to sine x sine y. And I've solved it on various grids of 10, 14, 20, 40, and 56. And that's 10, 40, 14. I'm plotting here the total error. The error, that's the difference between the numerical solution and the analytic solution, because I know the analytic solution of this test problem, as a function of delta x to the fourth. And there's a beautiful linear line. So it increases with those particular size grids at delta x to the fourth with a coefficient of 0.27. And that means that with a 20 by 20 grid, I get 6-figure accuracy with this fourth order scheme, compared with the original second order method, where I was only getting 3-figure accuracy. So, this is much more complicated, but it's much more accurate. So if you're in a situation where you need more accuracy, and you're prepared to invest in the complication, which means complicated code, which means more opportunities for it to go wrong, there are opportunities of getting something more accurate. Right, so that's for the Poisson equation. Here I'm saying that for the diffusion equation, so I think this is du by dt, 2 x derivatives of u. There are errors in forward time stepping which are proportional to, so if you want to solve the diffusion equation in a simple form, when you use forward time stepping, you get errors which are proportional to 2 derivatives. times delta t squared. There are errors like that. And similarly, if you use central differencing here, you will get errors which are delta x squared u x x x. And there are the coefficients which are very important, which I've forgotten, so I can't do it in front of you. And then what the trick is, you use this equation to find out that UTT is equal to UXXXX. So this term is equal to that term. And the result, if you use that information, the transparency is telling me what the coefficients are, but never mind. So you can change the difference. So this is the first order time derivative that u at the next time level n plus 1 is equal to the previous time level un plus delta t times the second derivative. But I'm using the second derivative at the new time step as well as the old time step. And this magic at 12th is this trick here. So that turns out to be fourth order accurate. It's fourth order accurate in delta x and second order accurate in delta t. Okay, so there are these, this is a compact version of higher accuracy of the diffusion equation. And it's getting quite complicated. So another issue in finite differencing, also is an issue in finite elements too, is advection. The term u dot grad of anything like u itself or perhaps temperature is about propagating information in the direction of u. Central differencing, which will use the point in front and the point behind, that's a nice accurate form of grad u. Unfortunately, it is it's using information, if the velocity is positive, it's using information where we're going to tell us what the value is. That's nonsense, isn't it? I'm using the answer to tell you what the answer is. I should only use information at I and before I at I minus 1. So this is a case where we should use first order differencing, one-sided differentiation. So to propagate information, we should use, if the velocity is positive, we should use the information at the current point and one point before. Or if u is negative, this is the complication, u may be positive and negative in our solution. If u is negative, we use the current information and the information we've come from, which is the point in I plus 1. Okay, and that's, so this is nicely propagating information. It's not using information where we're going to tell us how to get there. But it's only first order accurate. Okay, so you can do better. We can use our one-sided derivatives, which are second order accurate. So this is what you do if the velocity is positive. We can use information at I minus 1, and I minus 2. So it's a second order accurate one-sided derivative. And if u is negative, we can use information at the current point, 1 point plus and 2 points plus, because we're going backwards. And that will be second order accurate. But we have a wide numerical molecule. So they're not good ideas, wide numerical molecules. There's a compact form, which is nearly right. So this doesn't quite propagate. This doesn't quite propagate information downstream. It does use a bit of upstream information in certain circumstances. So this is written out for u and v being positive. So I use, okay, so I have to go through what's happening here. So this is the middle point is a point of interest. And here I'm using the point before. But I'm also using some information from where v is coming upwards, at the current point, at the point before, that's good, but the point in advance. So it all hinges on the ratio of u to v of whether this is, if I'm going sideways fast enough compared with coming up, that will be in upstream. Okay, so I do it again up for v. So for v, we're going the current point and the point where we've come from, and not the point where we're going to. That's good. And I'm using, there must be an error. No, it's probably right. But I'm using information that's coming sideways, because u is positive, at the current level, which is good. What is below us, which is good. But what's above us? Okay, so it is a matter of, can I go up faster than I can go sideways? So that is upstream. Right? So it's nearly upstream. And that's the expression when u and v are positive, so there are different expressions when the signs change. So 4 different things. This is getting complicated to code if you've got 4 options. It's not good for making very fast programs if you have to make big choices. So every time you make a choice, it tends to make it difficult to go to pipe the line. Well, it's just difficult, right? Okay. So I've been talking all the time about Cartesian geometry, square geometry, where we've got Cartesian coordinates and equispaced is nice. But of course, there are lots of problems we solve where we're interested in spheres, well, interested in cylinders. Spheres are even worse. And if your boundary is a nice, simple shape, like a cylinder or a sphere, you would be rather silly not to use cylindrical or spherical polars. So they are good orthogonal. There are good orthogonal coordinates, polar coordinates at work. If you have a slightly and there are, I think there's some 12 different geometries which have orthogonal coordinate systems, like ellipsoidal and hyperbolics and things like this. And there's bispherical polars. They're orthogonal coordinate systems. If there's orthogonal coordinate systems, you should use them, because it's like central differencing. It gives you good accuracy. More than that, I have twice in my life used non-orthogonal coordinate systems, and then it's very unpleasant, because there are things called co- and contravariant vectors and tensors, and you have to understand them. So the relativists understand them, but not fluid dynamicists. And it turns out the divergence and gradients, one is co and one is contra. So you have to flip from the co information to the contra information to work out what the divergence of the gradient is. It is very unpleasant. So it's a bad idea, non-orthogonal coordinates. Okay, if you want to increase the resolution, then a very good idea is to stretch the grid. So you may think it's a good idea to have non-equispaced points, and I'll go around putting the points down as I like, and have some general non-equispaced points. If you have non-equispaced points, you don't get second-order accuracy. If you use a stretching formula that we represent x non-uniformly by points, by a function x of psi, and the psi are uniformly equispaced, then you can arrange to be central differenced in terms of psi. So you can restore your central difference, higher accuracy, if you use a stretching function. The stretching function has to have enough derivatives. We normally use functions that have got all derivatives, so there's no difficulty. And you have to stretch x and y different, possibly with different functions, but independently. And that means that if we have our square, we'll have lots of points here, and then this over there. And equally, we may have lots of points down here, and we'll stretch like that. In order to get a good resolution in this corner, we've got a good resolution all the way along there and all the way along there, and you may not want a good resolution there and there, but it's probably worth the price of having this. This is an orthogonal coordinate system, and it's equispaced in the transform variables psi and eta. So you have to weigh the advantages. Are you going to be nicely equispaced with second order accuracy, resolving things you don't want to know about? It may not cost too much. So the alternative is to do something like this, is to have extra resolution where you want it. So there's a blue square, and then in the corner there is a green square, and in the corner of that there's a red square. So this looks good, that I can get higher resolution in the corner. The difficulty of this sort of approach is how do you transfer the extra information you have in the red high resolution onto the next resolution down, which you've got less points to absorb all this data. And then when you've got it on the green points, you've got a lot of information here. How do you transfer it onto the blue points? You've got this unnecessary information, which you don't want to throw away, because equally, when you go from the coarse blue resolution down to the green info, you need information halfway along those things. Where are you going to get that from? And the way you get that extra information, or you lose that extra information, is a big source of error, and it means the approach doesn't work. So this embedded higher resolution is difficult. Actually, with finite elements, you can do quite well with having the elements getting smaller in one place. But it is non-equispaced grids, so there's an error, order of magnitude in the error gone missing. Okay. So it's nice to have a fine resolution in some places. Or if you're using polar coordinates, there is a fine resolution you can't avoid. At the poles, there is a crowding of the points. So we have a nice resolution out here, but right at the pole, the coordinate catastrophe, there is a very fine resolution, and the finest grid is equal to the smallest r times the smallest change in theta. So it's quadratic in smallness. And we had constraints on our time stepping that the time step had to be less than a quarter times delta x squared. Delta x squared minimum, we have to worry about the smallest x and the largest u, or the smallest x divided by the biggest u in that area. But the smallest x, delta x, is this r minimum, which is delta r times delta theta. So we suddenly get pushed to a very small time step. On the sphere, there are a lot of people who are interested in what happens in a spherical annulus, who are interested in the internal flow of the Earth, the flow of the core. That's for continental drift. That's the mantle, isn't it? Well, the mantle is a viscous fluid, and you want perhaps like to study that annulus of how does the mantle move for continental drift, and then the outer core inside the mantle is molten. There's a lot of molten iron in it, which generates the magnetic field, the Earth's magnetic field. You may want to study that. So there's another spherical annulus, and people have nicely developed a system of, think about a cube with 6 sides, and then you put a Cartesian grid on those 6 sides, and then you sort of bend it nicely into a sphere. So you end up with the same size squares, and it's just the corners which have awkwardly got 3 lines coming to the corner rather than 2 crossing. So there's only a couple of special points, but they're nice big grids. There's not this very fine grid at the middle. So you can avoid the coordinate catastrophe by patching different grids for different places. So if you want to solve this problem here, you could just slap a Cartesian grid on the middle bit there. Patching it to the polar grid outside is a mess, equals errors. Okay, and then very often we're told to solve flow past the sphere in an infinite domain, and computers don't go very far to infinity. So an infinity ought to be about 3. So how do you bring infinity in? You use stretches. So an exponential stretch will mean, so if we only go to psi equals 10, we have gone out to x is what, 1,000, a couple of thousand. Equally, so that means you can go a long way to infinity, your furthest point, which is actually quite small in the value of the transform variable psi. Alternatively, this transformation psi divided by 1 minus psi will actually map 0 to infinity onto 0 to 1. And then you grid your 0 to 1. There are actually much better things to do is to understand a bit of physics. If you understand the physics, what is happening in the far field for flow past a sphere is you are seeing a point force, the drag, in a uniform flow. We can go and look up Ocean's solution for a point force in a uniform flow, and then we can apply that at x equals 5. There's an unknown coefficient because we don't know the drag. We're trying to calculate the drag. At high Reynolds numbers, that doesn't work because there's a long downstream wake which goes a distance. Is it 1 upon the Reynolds number or 1 upon? Yeah, I think it's 1 upon the Reynolds number. So your grid does have to go downstream by 1 upon the Reynolds number to get the. Okay. There was a little embarrassment at the end of last lecture. When I worked out the force on my box, I could work out the viscous force on the top. But now, because I've got the pressure, I can work out the viscous force on the bottom. And the pressure force is on the side. And because it's a steady state and there's no creation of momentum, there's no body force, it should be the force on the top is equal to the force on the top plus the force on the bottom plus the force on the side should cancel to 0. And it didn't quite get to 0. It was within a percent of 0. You may want to make it exactly 0. And you may want to conserve your numerical scheme, which is an approximation to the momentum equation. You would like your approximate equation to conserve momentum exactly. That's called a conservative scheme. Sorry, global momentum. So it's not conserving momentum at each point because it's only an approximation of the governing equation at each point. But you'd like it to solve to be such that the total momentum is always 0. And to do that, you need two ideas. You need a formulation of the governing equations, which is called a conservative formulation, and then you need to apply it to volumes of fluid. And there is a finite volumes of fluid. Then there is a whole area of numerical methods called volume of fluid, which adds certain extra things to do with free surfaces. So you can recast the Navier-Stokes equation into a conservation of momentum form, which says the momentum changes in time due to a divergence of the flux of momentum. And the flux of momentum, because I'm saying there's no body forces, otherwise we would create momentum. I'm saying that the body forces, the flux of momentum is there's a Reynolds stress, which is velocity carrying momentum sideways. There's an isotropic pressure, and then there are viscous stresses. So the divergence of this total stress T will change the momentum in time. And then if I were to integrate this equation, if I integrate this equation over the whole domain at time equals, in the steady state, so in the steady state there's no time derivative, if we integrate that globally, we would get the integral of the stress around the boundary, which is exactly the force on the top has to be equal to minus the forces on the sides and the bottom. So it would be exactly right. So that's the conservative form of the differential equation. And then applying it to the staggered grid, where I hold the velocity half point up, the horizontal velocity halfway up, so it's the inflow. The vertical velocity is held half a point to the side, so it's the inflow of vertical velocity, and pressure's held in the middle. I now have to hold the stresses somewhere, and it turns out you hold the diagonal stresses like pressure, because there's the diagonal of the stress tensor, and the tangential components are held, sorry, this is at the ij point. Yeah, that point there. And then to work out how the momentum is changing in time, the horizontal momentum, you apply conservation of momentum to this box. So you say the momentum at time level n plus 1 is the momentum at time level n plus the contribution of, say, the pressure forces there and there, but it's now actually not, it's the xx component of the stress. The difference between the value there and there tells me the stress sideways, and then the tangential forces which are pushing in that direction, the difference between the value there and there. So the momentum at the new time step is the momentum at the old time step plus delta t. This is a minus sign because the way the equation was, and it's the pressure, it was the difference between the pressure there and there is changing the momentum here, but it's now become the stress, the xx component of the stress, the difference between there and there, the I plus a half, I minus a half. And then the difference of the tangential stress is pulling it sideways between the bottom and the top, between j plus 1 and j. Right, so that's the conservative form applied to a finite volume of fluid, and I have to come up with expressions for those stresses. Okay, so I will show in a minute. What we have to do, if we integrate this over several blocks, so there's this block here, there's another block to the side, there's another block to the side. If we add up all the contributions, then it's clear that the stress pushing in there is cancelled by the stress pulling in there. So we end up with just the xx, the difference between the xx at that wall and the xx at that wall. That's the difference of the pressure on the two walls. And it's not quite because it misses by a half block. And to deal with the final half block from the internal point onto the boundary, you see we've only gone halfway towards the next point in the boundary. You need to have a boundary condition that tells you about what the stress Txx is at the ghost point outside the domain. And that turns out to be effectively telling you what the pressure is at a point, half point outside. So you have to get the pressure correct on the ghost point outside in order to get, and then we work the pressure on the boundary as being the pressure half point in, the average of half a point in and half a point outside. These staggered grids are complicated. Right, and these are the horrible expressions for these stresses. So the first term here is rho u squared, but at the middle point I don't have u, so I have to take the average of u to some. Right, so I'm trying to find out Txx here as rho u squared, but I have u there. So I have to take the average between u there and u there to find u in the middle. So that's the mess that's going on here. I'm taking averages of velocities to move them from the points where they're on the staggered grid to the points where the stress is supposed to be evaluated. The pressures are exactly in the right place, so the pressure occurs very simply, and equally the viscous stresses, they are simple differences. But getting the Reynolds stresses, I have to average the velocities from where they are to where I'd like to work out the stress. So the expressions, when you give all these subscripts around, and writing a numerical molecule would have been much better, but then you're writing a numerical molecule squared, and you start to worry, this is a matrix operation or something. So we didn't do that. Okay. When you're in non-Cartesian coordinates, the idea of conservation also crops up. So for del squared phi, Laplacian of phi in radial, in polar cylindrical, this is in spherical polars, is 1 upon r squared, the r derivative of r squared. And then there's some theta terms which are, there's an exact, you will have used many times you just multiply out the derivatives, differentiate the r squared and get 2 times the first derivative. Numerically, you should not use the second one. You should use the first one because it's a conservation form. And it's just as easy to code the conservation form as this analytically equivalent, but numerically not equivalent. So when you work out, when you make a discrete version of this, it will be this r squared phi by dr at half a point forward minus half a point back. That's divided by the r at the point of interest. That's the first derivative. So we're taking this first derivative, 1 upon r squared, the first derivative here, and then we work out the first derivatives as being 1 point in front, 1 point behind, but then multiplied by r at the half point. And if you substitute that all in, you'll find it doesn't give the numerical version of this. And this is to be preferred because, again, when you integrate it all up, it gets exactly the right thing on the boundary. Okay. So I've been interested in just the flow of a single liquid. I've also quite interested in my research in two-phase flow, having air and water, or two different liquids. And there is an approach to computing that two-phase flow, which is to say, well, it's all one fluid. It's all fluid, isn't it? Let's call it one fluid. Use this volume of fluid approach, and you allow the density to be a function of position and the viscosity to be a function of position. The value is, what liquid are you in? What fluid are you in? Are you in water or are you in air? So use the density depending on where you are. But if you have this conservation formulation, it will work right. How you deal with surface tension in between gets us into nasty messes, which I will talk about in the special topics. So there is a volume of fluid approach, sometimes called a one fluid method, which uses this conservation idea. And then finally, there are various versions of U dot grad U. So these are analytically equivalent versions of U dot grad U. And you may want to code one of them rather than another one, when you're writing a numerical version, depending on what you want to do. So the divergence of UU, I've just been using, divergence of the Reynolds stress gives us a conservation of momentum. The equivalent, it's the gradient of a half U squared minus U cross omega, is sort of conserves angular momentum. It's a good idea if angular momentum is important to you. And then this strange half of the first term plus half of this term conserves energy. So, and it's called the skew symmetric form, that last form, and I challenge you to work this out. So this is, if you take a scalar product of this, that's how we form the energy equation. We take U dot with this to get the energy, the kinetic energy expression. Then you get this now. The subscripts in this are the components, U, V, W. The upper indices are the positions. And J varies through values 1, 2, 3. And so if you look at this long enough, you can decide that when you add up across a grid, when you add the contributions of this term all the way across the grid, then the first term will cancel with the fourth term, and the second term will cancel with the third term. Okay, so this is an exercise for the students, to just get your mind, what on earth is happening with all those subscripts. And you might want to write it out in detail with U and V at position something and something. In a one-dimensional example would be a good idea to start with. Okay, that's it. Oh, just one question to you. At what stage in India, well, what are you using for the cross product? Do you use this caret or do you use a cross now? You use a cross, good. That's what I was taught. And then the pure mathematicians came in and said we couldn't do that. We had to use carets. And they won for about 20 years. And now I think we've gone back into crosses. I'll change it to cross. Thank you.